welcome to Breadth First Search, BFS. So this is our first search algorithm we're going to actually be doing a deep dive into. I think this is an algorithm that you are perhaps very likely to have actually seen in one of your introduction to computer science classes. It's often used as an example just to get used to writing algorithms and interacting with nodes and computers and things like that. If you haven't, that's all good. Breadth First Search is extremely easy. So let's talk about what the actual search strategy is that's going on here. If you remember from last video, the search strategy is just the order in which we're going to expand nodes, the order we're going to look at nodes and choose nodes in the open list to grow the search tree next. Okay, so the strategy of Breadth First Search really is that we are going to expand nodes at each level of the search tree at a time before moving downward. Okay, so BFS is pretty simple in that regard. We're just going to be expanding radially at each level, right? So this is level 0, level 1, level 2, and we have to expand all of the nodes in a level before we then continue downwards to the next one. So essentially this strategy, if you think about it, this is actually just first in, first out, which you may be familiar with from things like queues, right? So the very first node that pops in is going to be the one that's expanded first, is the first one to also come out, to pop out. So, okay, at the very beginning, very boring, right? The only thing in the open list is the root node A. Okay, so we are going to pop this out, and then we are going to expand A and generate its children. So we find both B and C now. So unlike the dashed lines, these are now solid. I'm indicating that they are actually generated. Okay, so both B and C now get chucked into this list. They're both at the same level 1, right? They have a depth of 1. In this situation, whether you expand or put in B or C first, this is up to tie breaking. This does not matter. The order is the same as long as they're both ranked similarly, then we're good to go. That's BFS. Tie breaking can help us in different ways, but that's something we'll deal with later. Okay, great. So now we've grabbed both B and C. We are going to continue the algorithm. So we're going to pop the first one out of the queue. It was the first one in, it's the first one out. That's our FIFO, right? So B is popped out. C is still in our open list, okay? But now we're going to also find that when we expand B, we generate its children, and we find the new nodes D and D. So both D and E then get added into our list. Again, the order of these two together is up for debate, but it's pretty standard. You can tie break that either way you want. Okay, so at this point we've now expanded B. We just continue the algorithm, first in, first out. The next one is C. So we still have D and E in our list, but now we do the same thing for C. We generate its children, F and G, and then we're going to add these to the search list as well. Okay? Oops, why did I do that? That's better. So now we have D, E, F, G in our open list. So essentially what's happened, right, is if we follow this first in, first out ordering, the first things we find are going to be at the level. So you'll see that because B and C were put in early, they will always be before D and E, right? They were at the previous level. They will always be expanded first. This is how we get that very generic breadth first behavior we're looking at. You'd continue through, you'd expand all of these, the search tree would grow if it can. Ta-da. That is essentially how BFS is going to work. So one thing I want to do now though is also just let's have a look then after we've described the algorithm. I think it makes a lot of sense. It's very easy to understand how it works. But let's discuss the properties of the algorithm. Okay, so this is a callback now to the previous video on things such as we're going to be looking at space and time complexity, as well as the completeness and optimality of our algorithms. Okay, so the first one then is completeness. Does breadth first search guarantee that if a solution exists in here, we'll be able to find it? Okay, I'm going to use, for convenience, the letter G as our goal node. Okay, I've highlighted in yellow. This is what we're looking for. So, you know, when you consider completeness, you don't get to just choose one example. I'm just using this as something to drive our discussion. It would, in order for an algorithm to be complete, no matter where the goal node is, you need to be able to find it. So it's pretty easy to see, I think, that as we progress radially outwards, if the goal was in level 1, it'll eventually be expanded, right? If the goal was in level 2, it'll eventually be expanded after level 1, and so forth. So it's pretty easy to see that BFS is just complete. This is happy days. Okay? Now let's talk about optimality though. So this is essentially, does BFS guarantee that we find the optimal solution? This one can be a little tricky. So I think intuitively, right, you're probably just thinking yes. And the answer is realistically yes, but I'm going to chuck an asterisk in there, okay? So why am I chucking in an asterisk? Because we're expanding by level. G will be expanded, congratulations, but perhaps there were multiple goals. What happens if there was a goal 2 further down at a lower depth, at a lower level in the tree? We're saying BFS is expanding by levels. We'll find this one, we'll find the shallowest goal first every time. Okay, and we're going to return that because, hey, we're done, right? So the reason this is a little dangerous is only the fact that we've made an assumption here that cost is related to depth. Okay, so when we have a cost on the edges as we're traversing and expanding our nodes, as long as that cost is associated, directly correlated with the depth of the solution, then BFS is optimal. So this is pretty much always the case. But we really have to be careful when they are non-uniform costs, because then all of a sudden different versions of the path might be, I don't know why I wrote 2, might be substantially cheaper, okay? So going down here at a cost of 1, 3, 4, so the cost of 4 on this path, this goal would be better than having a really high cost edge. So yeah, essentially BFS is optimal, but we just need to be really careful about that. So now we're going to move on to the time and space complexity that we're going to be describing in terms of a big O notation, which is something you might be familiar from other computer science subjects. But essentially, we're talking about how the search space is going to grow with the input size, okay? So the terminology we use here is often graph terminology, so we could describe this in terms of the number of vertices and edges in our graph. But another way to do this is using the notation we defined in the earlier video, is to use both the branching size and the depth, okay? So I think that's a good starting point. So here we can talk about, in terms of the space complexity, this is essentially how many nodes there are, right? What's the actual size of the tree? How many things do we have to store? How much information do we need to store? Then the actual, memory size. This would be kind of computed as well based on the actual implementation. But in terms of the theoretical analysis of space complexity, it really is just like, hey, what's the size of the tree? And so we always try to talk about the time and space complexity in terms of the worst case scenario, okay? Because that gives us a better idea of how to actually bound the algorithms. So in this case, we're seeing that the number of nodes, when we finally find the goal is going to be at some depth d, okay? We will have had to have looked at every node along the way. So how can we try to reason over how many nodes that would have been? So at the very beginning, at level 1, right, okay, there's one node. Pretty simple. At the next one, we see that there's now 2. But if I'm going to describe that in terms of the branching factor, we're saying, hey, how many things can I do from the root node? Well, b, right? So B is 2 in this case, but we can express it as B in a generic sense. In the next layer, well, we now have, for all of those B nodes, each of them can also spawn an additional B nodes. So here, B squared comes in as our next term. We can write out this series generically such that when we finally get to the goal node, right, it will have B to the power of whatever the depth of the solution was. So B to the D. Now, because we have a sum of polynomials here, when we're talking about big O notation, the final term is the one that's going to dominate, and that is what corresponds to big O notation, right? Like the B to the D term dominates the rest. It gives us the most informative idea over the actual growth of the algorithm and its properties. So therefore, the space, in this case, both the space and the time complexity, both grow according to this. The way the algorithm progresses and the space it requires is the same, right? And so yeah, we would describe both of these as O of B to the D. Now, in the next videos, we'll start to compare this against DFS, and we'll see maybe that there are beginning to be differences in the properties that they offer, and as well, how much space and time they're going to take to find a solution. So join me for that as we move forward in our algorithm journey.